Question 101. Your company is building a new architecture to support its data-centric business focus. You are responsible for setting up the network. Your company's mobile and web-facing applications will be deployed on-premises, and all data analysis will be conducted in GCP. The plan is to process and load 7 years of archive.csv files totaling 900 terabits of data and then continue loading 10 terabits of data daily. You currently have an existing 100 megabytes internet connection. What actions will meet your company's needs? A. Compress and upload both archived files and files uploaded daily using the XUTIL Euro M option. B. Lease a transfer appliance, upload archived files to it, and send it to Google to transfer archived data to cloud storage. Establish a connection with Google using a dedicated interconnect or direct peering connection and use it to upload files daily. C. Lease a transfer appliance, upload archived files to it, and send it to Google to transfer archived data to cloud storage. Establish one cloud VPN tunnel to VPC networks over the public internet, and compress and upload files daily using the XUTIL Euro M option. D. Lease a transfer appliance, upload archived files to it, and send it to Google to transfer archived data to cloud storage. Establish a cloud VPN tunnel to VPC networks over the public internet, and compress and upload files daily. The best approach is B. Lease a transfer appliance, upload archived files to it, and send it to Google to transfer archived data to cloud storage. Establish a connection with Google using a dedicated interconnect or direct peering connection and use it to upload files daily. Explanation. This option is the most suitable for meeting the company's needs, considering the volume of data and the existing 100 megabytes internet connection. One transfer appliance for archived data, with 900 terabits of archived data, uploading over a 100 megabytes internet connection would take an unreasonably long time, even with compression. A transfer appliance is a secure, efficient, and reliable way to transfer large datasets to Google Cloud Storage. Once the data is uploaded to the appliance, it is physically shipped to Google for ingestion into cloud storage, eliminating the bottleneck of the internet connection. 2. Dedicated interconnect or direct peering for daily data. Transferring 10 terabits of data daily requires a high bandwidth, low latency connection to Google Cloud. A dedicated interconnect or direct peering connection provides up to 100 gigabits per second bandwidth, which is necessary for handling large daily transfers efficiently. This approach ensures reliable and predictable performance compared to a cloud VPN tunnel or standard internet connection. 3. Scalability and reliability. This solution combines a one-time transfer appliance for the archived data and a scalable, high-performance connection for ongoing daily uploads, aligning with the company's data-centric business focus. Analysis of other options. Option A suggests compressing and uploading the archived and daily files using the XUTIL M option. This approach is impractical because transferring 900 terabits of data over a 100 megabytes connection would take years, and uploading 10 terabits daily would strain the connection significantly. Option C proposes using a transfer appliance for archived data and a cloud VPN tunnel for daily uploads with compressed files. While a transfer appliance is suitable for archived data, a cloud VPN tunnel over the public internet is insufficient for transferring 10 terabits daily due to bandwidth limitations and potential reliability issues. Option D is similar to option C but omits compression for daily uploads. This further increases the daily data transfer challenge over a cloud VPN tunnel, making it an even less viable solution. Conclusion. Option B is the best choice because it addresses the challenges of transferring large volumes of data both initially and daily. It leverages the most efficient tools and connections available, ensuring scalability, reliability, and alignment with Google Cloud best practices. Question 102. You are developing a globally scaled frontend for a legacy streaming backend data API. This API expects events in strict chronological order with no repeat data for proper processing. Which products should you deploy to ensure guaranteed once FIFO, first in, first out, delivery of data? A. Cloud Pub Sub alone. B. Cloud Pub Sub to Cloud Data Flow. C. Cloud Pub Sub to Stackdriver. D. Cloud Pub Sub to Cloud SQL. The best approach is B. Cloud Pub Sub to Cloud Dataflow. Explanation. The legacy API requires strict FIFO, first in, first out, delivery of events with no duplicate data. Here's how this solution addresses the requirements. 1. Cloud Pub Sub provides reliable, global, and scalable message ingestion and delivery. However, Pub Sub does not natively guarantee message ordering or eliminate duplicates by itself. While it ensures at least once delivery, additional processing is required to enforce strict ordering and deduplication. 2. Cloud Dataflow, a fully managed stream and batch data processing service that allows for custom transformations, including enforcing FIFO ordering and deduplication. Using Dataflow, you can process Pub Sub messages, implement windowing or sequencing to preserve chronological order, and eliminate duplicate events before sending them to the legacy API. This combination ensures guaranteed once FIFO delivery while handling the scale and complexity of global front-end data ingestion. Analysis of other options. Option A suggests using Cloud Pub Sub alone. While Pub Sub is scalable and reliable, it does not guarantee strict FIFO delivery or deduplication. This makes it unsuitable for the requirements of the legacy API. Option C combines Cloud Pub Sub with Stackdriver, now called Cloud Monitoring. Stackdriver is a monitoring and logging service and does not provide any functionality for enforcing FIFO or eliminating duplicates. Option D pairs Cloud Pub Sub with Cloud SQL. While Cloud SQL can be used to persist data and process it in sequence, this approach is not scalable for a globally scaled frontend. Additionally, managing message ordering and deduplication in Cloud SQL introduces unnecessary complexity and operational overhead. Conclusion. Option B is the best choice because it leverages Cloud Dataflow to process and enforce FIFO ordering and deduplication of events received from Cloud Pub Sub. This solution meets the requirements of the legacy API and is aligned with Google Cloud best practices for scalability and reliability. Question 103. Your company is planning to perform a lift and shift migration of their Linux RHEL 6.5 Plus virtual machines. The virtual machines are running in an on-premises VMware environment. You want to migrate them to Compute Engine following Google recommended practices. What should you do? A1. Define a migration plan based on the list of the applications and their dependencies. 2. Migrate all virtual machines into Compute Engine individually with Migrate for Compute Engine. B1. Perform an assessment of virtual machines running in the current VMware environment. 2. Create images of all disks. Import disks on Compute Engine. 3. Create standard virtual machines where the boot disks are the ones you have imported. CA1. Perform an assessment of virtual machines running in the current VMware environment. 2. Define a migration plan, prepare a Migrate for Compute Engine migration runbook, and execute the migration. D1. Perform an assessment of virtual machines running in the current VMware environment. 2. Install a third-party agent on all selected virtual machines. 3. Migrate all virtual machines into Compute Engine. The best approach is C. Perform an assessment of virtual machines running in the current VMware environment. Define a migration plan, prepare a Migrate for Compute Engine migration runbook, and execute the migration. Explanation. This option follows Google Cloud's recommended practices for a lift and shift migration of virtual machines from an on-premises VMware environment to Compute Engine. 1. Assessment of virtual machines. Evaluating the current VMware environment is essential to understand the resource requirements, dependencies, and compatibility of the virtual machines. This step ensures that the migration plan is well-informed and tailored to the workload's needs. 2. Migration plan and runbook. Creating a migration plan that documents the steps, dependencies, and timelines helps ensure a smooth transition. Preparing a Migrate for Compute Engine runbook provides a detailed guide for executing the migration, including configurations, validations, and post-migration checks. 3. Migrate for Compute Engine. This tool is purpose-built for lift and shift migrations of virtual machines from VMware environments to Google Cloud. It automates the migration process, minimizes downtime, and handles complex tasks like image conversion, disk import, and compatibility adjustments. This structured approach ensures that the migration is efficient, minimizes risks, and adheres to best practices. Analysis of other options. Option A suggests migrating all virtual machines individually with Migrate for Compute Engine without defining a migration runbook. While Migrate for Compute Engine is the correct tool, skipping the preparation of a runbook risks overlooking dependencies, causing potential disruptions. Option B involves creating images of all disks, importing them to Compute Engine, and creating virtual machines manually. This approach is labor-intensive, error-prone, and lacks the automation and efficiency provided by Migrate for Compute Engine. Option D involves installing a third-party agent on all virtual machines. Using a third-party tool is unnecessary when Migrate for Compute Engine is specifically designed for VMware to Compute Engine migrations. This option also adds complexity and potential security concerns by introducing an external dependency. Conclusion. Option C is the best choice because it combines a comprehensive assessment, structured planning, and the use of Migrate for Compute Engine, aligning with Google Cloud's recommended practices for a reliable and efficient lift and shift migration. Question 104. You need to deploy an application to Google Cloud. The application receives traffic via TCP and reads and writes data to the file system. The application does not support horizontal scaling. The application process requires full control over the data on the file system because concurrent access causes corruption. The business is willing to accept a downtime when an incident occurs, but the application must be available 24/7 to support their business operations. You need to design the architecture of this application on Google Cloud. What should you do? A. Use a managed instance group with instances in multiple zones, use Cloud File Store, and use an HTTP load balancer in front of the instances. B. Use a managed instance group with instances in multiple zones, use Cloud File Store, and use a network load balancer in front of the instances. C. Use an unmanaged instance group with an active and standby instance in different zones, use a regional persistent disk, and use an HTTP load balancer in front of the instances. D. Use an unmanaged instance group with an active and standby instance in different zones, use a regional persistent disk, and use a network load balancer in front of the instances. The best approach is D. Use an unmanaged instance group with an active and standby instance in different zones, use a regional persistent disk, and use a network load balancer in front of the instances. Explanation. This architecture meets the application's requirements, considering the constraints of full control over the file system, avoiding concurrent access to prevent corruption, and ensuring 24/7 availability with acceptable downtime during incidents. Unmanaged instance group with active standby instances. Since the application does not support horizontal scaling, using an unmanaged instance group with active and standby instances in different zones is appropriate. This setup allows for manual failover or orchestrated failover when the active instance fails, ensuring availability. Regional persistent disk. A regional persistent disk provides synchronous replication of data across two zones, ensuring that the standby instance has access to the same data as the active instance. This is crucial for maintaining consistency and avoiding corruption during failover. Network load balancer. A network load balancer is suitable for handling TCP traffic and forwarding it to the appropriate instance. It can redirect traffic to the standby instance during failover, ensuring continuous operation. Downtime during incidents. While failover may involve some downtime, this is acceptable to the business, as long as the application is available 24/7. Analysis of other options. Option A suggests using a managed instance group with instances in multiple zones, Cloud File Store, and an HTTP load balancer. While Cloud File Store can provide shared file storage, it does not meet the requirement of preventing concurrent access, which may lead to data corruption. An HTTP load balancer is also unsuitable for TCP traffic. Option B is similar to option A but replaces the HTTP load balancer with a network load balancer. This improves traffic handling for TCP but still relies on cloud file store, which does not meet the application's file system control requirements. Option C uses an unmanaged instance group with active and standby instances and a regional persistent disk but pairs this setup with an HTTP load balancer. An HTTP load balancer is designed for HTTP/S traffic, not TCP traffic, making it an inappropriate choice for this application. Conclusion. Option D is the best choice because it uses an architecture tailored to the application's requirements. It ensures proper control over the file system, avoids data corruption, and provides 24/7 availability with failover between zones, leveraging a regional persistent disk and a network load balancer for efficient and reliable operations. Question 105. Your company has an application running on multiple compute engine instances. You need to ensure that the application can communicate with an on-premises service that requires high throughput via internal IPs, while minimizing latency. What should you do? A. Use OpenVPN to configure a VPN tunnel between the on-premises environment and Google Cloud. B. Configure a direct peering connection between the on-premises environment and Google Cloud. C. Use Cloud VPN to configure a VPN tunnel between the on-premises environment and Google Cloud. D. Configure a cloud-dedicated interconnect connection between the on-premises environment and Google Cloud. The best approach is D. Configure a cloud-dedicated interconnect connection between the on-premises environment and Google Cloud. Explanation. Cloud-dedicated interconnect is the most suitable solution for scenarios requiring high throughput, low latency, and communication via internal IPs between on-premises and Google Cloud environments. 1. High throughput. Dedicated interconnect provides bandwidth options up to 10 gigabits per second per link, with the ability to bundle multiple links for higher throughput, making it ideal for applications that require high data transfer rates. 2. Low latency. Since dedicated interconnect establishes a physical connection between your on-premises network and Google's network, it significantly reduces latency compared to VPN-based solutions. 3. Internal IP communication. Dedicated interconnect supports direct communication using internal IPs, ensuring seamless integration between on-premises services and applications running on Google Cloud. 4. Reliability. Dedicated interconnect offers SLA-backed uptime and performance, ensuring consistent connectivity for business-critical applications. Analysis of other options. Option A suggests using OpenVPN to configure a VPN tunnel. While OpenVPN can enable communication between environments, it is a software-based solution with limited throughput and higher latency compared to dedicated interconnect. It is less suitable for high throughput and low latency requirements. Option B involves configuring a direct peering connection. Direct peering provides connectivity to Google's public IPs but does not allow communication using internal IPs. This makes it unsuitable for the given requirement. Option C recommends using Cloud VPN to configure a VPN tunnel. Cloud VPN is a cost-effective option for secure communication, but it has lower throughput limits, up to 3 gigabits per second per tunnel for high-availability VPN, and higher latency compared to dedicated interconnect. It is more suitable for moderate workloads or as a backup for dedicated interconnect. Conclusion. Option D is the best choice because it offers high throughput, low latency, and internal IP communication, all of which are critical for the given requirements. Dedicated interconnect is the most reliable and efficient solution for integrating on-premises services with applications running on Google Cloud. Question 106. You are managing an application deployed on Cloud Run for Anthos, and you need to define a strategy for deploying new versions of the application. You want to evaluate the new code with a subset of production traffic to decide whether to proceed with the rollout. What should you do? A. Deploy a new revision to Cloud Run with the new version. Configure traffic percentage between revisions. B. Deploy a new service to Cloud Run with the new version. Add a cloud load balancing instance in front of both services. See in the Google Cloud Console page for Cloud Run, set up continuous deployment using Cloud Build for the development branch. As part of the Cloud Build trigger, configure the substitution variable traffic_% with the percentage of traffic you want directed to a new version. D. In the Google Cloud Console, configure traffic director with a new service that points to the new version of the application on Cloud Run. Configure traffic director to send a small percentage of traffic to the new version of the application. The best approach is A. Deploy a new revision to Cloud Run with the new version. Configure traffic percentage between revisions. Explanation. Cloud Run for Anthos supports built-in traffic splitting, allowing you to route a specific percentage of traffic to different revisions of your application. This approach aligns with best practices for safely deploying new versions in production by gradually exposing the new version to real traffic. 1. Deploy a new revision. When you deploy a new revision of your application to Cloud Run, it automatically creates a new instance without affecting the existing one. 2. Configure traffic splitting. In the Cloud Run settings, you can specify how much traffic should go to each revision, example 10% to the new version and 90% to the current version. This enables you to evaluate the new code's behavior in a live environment while minimizing the risk of a full rollout. 3. Evaluation and rollout. Based on the performance and stability of the new version, you can incrementally increase the traffic percentage until it fully replaces the old version. This strategy provides fine-grained control, reduces deployment risks, and ensures you can roll back if any issues arise with the new version. Analysis of other options. Option B suggests deploying a new service and adding a cloud load balancer in front of both services. While this approach can work, it introduces unnecessary complexity. Cloud Run already has built-in traffic splitting, eliminating the need for an external load balancer. Option C involves setting up continuous deployment using Cloud Build and configuring the traffic_% variable. While Cloud Build can automate deployments, managing traffic percentages through substitution variables in the build process adds complexity and lacks the flexibility provided by Cloud Run's native traffic splitting features. Option D suggests configuring Traffic Director for traffic splitting. Traffic Director is a service mesh solution intended for complex, large-scale, multi-service architectures. It is not needed for a simple use case like deploying a new revision to Cloud Run. Conclusion. Option A is the best choice because it leverages Cloud Run's native traffic splitting capabilities, which are designed for gradual rollouts and safe evaluation of new versions. This approach is straightforward, efficient, and aligns with Google recommended practices for managing deployments in Cloud Run for Anthos. Question 107. You are monitoring Google Kubernetes Engine, GKE, clusters in a cloud monitoring workspace. As a site reliability engineer, SRE, you need to triage incidents quickly. What should you do? A. Navigate the predefined dashboards in the cloud monitoring workspace, and then add metrics and create alert policies. B. Navigate the predefined dashboards in the cloud monitoring workspace, create custom metrics, and install alerting software on a compute engine instance. C. Write a shell script that gathers metrics from GKE nodes, publish these metrics to a pub subtopic, export the data to BigQuery, and make a Data Studio dashboard. D. Create a custom dashboard in the cloud monitoring workspace for each incident, and then add metrics and create alert policies. The best approach is A. Navigate the predefined dashboards in the cloud monitoring workspace, and then add metrics and create alert policies. Explanation. When managing GKE clusters and triaging incidents, the goal is to leverage tools that offer speed, ease of use, and integration with Google Cloud Services. Here's how this approach works. 1. Predefined dashboards in cloud monitoring. Google Cloud provides predefined dashboards in cloud monitoring that are tailored for GKE. These dashboards offer out-of-the-box visualizations for key metrics such as CPU, memory usage, pod status, and node health, making it easy to monitor the overall health of your GKE clusters. 2. Add metrics and alert policies. Once you have an overview of the predefined dashboards, you can fine-tune your monitoring setup by adding custom metrics if needed, example application-specific metrics, and setting up alert policies. Alerts allow you to be notified immediately when thresholds are exceeded or anomalies are detected, enabling quick triage of incidents. 3. Efficiency. This approach is straightforward and uses the built-in capabilities of Google Cloud Monitoring. It reduces the time spent manually gathering data or creating custom solutions, and it ensures that alerts are triggered automatically when incidents arise. Analysis of other options. Option B suggests using predefined dashboards, creating custom metrics, and installing alerting software on a compute engine instance. While this might work, installing alerting software on a separate instance is unnecessary when cloud monitoring provides native alerting capabilities. It adds complexity and management overhead without providing significant advantages. Option C suggests writing a shell script to gather metrics, publish them to PubSub, and use BigQuery and Data Studio for analysis. While this approach might work for highly customized use cases, it introduces significant overhead in managing scripts, data pipelines, and dashboards. It is far more complex than using cloud monitoring's predefined features and alerting tools. Option D involves creating a custom dashboard for each incident, which would require you to manually create dashboards every time an issue arises. This is inefficient and reactive rather than proactive. It also doesn't leverage cloud monitoring's predefined dashboards, which are designed to make incident triage quicker. Conclusion. Option A is the best choice because it uses predefined cloud monitoring dashboards, which are already optimized for GKE, and allows you to efficiently add custom metrics and alert policies for real-time incident triage. This approach minimizes complexity, maximizes the use of Google Cloud's native monitoring capabilities, and ensures quick detection of issues. Question 108. You are implementing a single cloud SQL MySQL second-generation database that contains business-critical transaction data. You want to ensure that the minimum amount of data is lost in case of catastrophic failure. Which two features should you implement? A. Sharding. B. Read replicas. C. Binary logging. D. Automated backups. E. Semisynchronous replication. The best features to implement are C. Binary logging and D. Automated backups. Explanation. 1. Binary logging. C. Binary logging is essential for ensuring minimal data loss in case of a catastrophic failure. It records all changes made to the database, example, inserts, updates, and deletes, which can be used to replay transactions and restore data up to a very specific point in time. This is particularly important in disaster recovery scenarios, as it allows for recovery from the most recent transaction that was committed before the failure. 2. Automated backups. Automated backups are crucial for regular, consistent backups of the database. These backups can be used to restore the database to a previous state, ensuring that data loss is minimized. Automated backups are scheduled by Cloud SQL and can be performed daily or at custom intervals, providing a robust recovery mechanism. Analysis of other options. Option A. Sharding. Sharding is a method for partitioning large databases across multiple servers, but it does not specifically help with minimizing data loss in case of failure. While sharding can improve performance and scalability, it does not directly address data recovery and disaster resilience. Option B. Read replicas. Read replicas are useful for scaling read-heavy workloads and improving the availability of data for read operations. However, they do not provide a direct mechanism for data recovery in case of catastrophic failure. They are typically used for load balancing and failover in read scenarios, not for minimizing data loss. Option E. Semisynchronous replication. Semisynchronous replication provides some guarantees for data replication between a master and replica, ensuring that the master waits for acknowledgement from at least one replica before committing a transaction. While it can improve data durability, it is still susceptible to data loss if the replicas are not up to date or if the replication setup fails. It is generally more useful in high availability scenarios but may not guarantee minimal data loss during catastrophic events like automated backups and binary logging. Conclusion. The best approach is to implement binary logging, C, and automated backups, D. These two features work together to ensure that you can recover the database with minimal data loss in case of a failure. Binary logging enables transaction replay for precise recovery, while automated backups provide periodic snapshots of the database for disaster recovery. Question 109. You are working at a sports association whose members range in age from 8 to 30. The association collects a large amount of health data, such as sustained injuries. You are storing this data in BigQuery. Current legislation requires you to delete such information upon request of the subject. You want to design a solution that can accommodate such a request. What should you do? A. Use a unique identifier for each individual. Upon a deletion request, delete all rows from BigQuery with this identifier. B. When ingesting new data in BigQuery, run the data through the Data Loss Prevention (DLP) API to identify any personal information. As part of the DLP scan, save the result to Data Catalog. Upon a deletion request, query Data Catalog to find the column with personal information. C. Create a BigQuery view over the table that contains all data. Upon a deletion request, exclude the rows that affect the subject's data from this view. Use this view instead of the source table for all analysis tasks. D. Use a unique identifier for each individual. Upon a deletion request, overwrite the column with the unique identifier with a salted SHA-256 of its value. The best approach is A. Use a unique identifier for each individual. Upon a deletion request, delete all rows from BigQuery with this identifier. Explanation. 1. Unique identifier for each individual. By assigning a unique identifier to each individual, such as a user ID or member number, you ensure that each piece of health data is traceable to the individual it belongs to. This allows for precise identification and deletion of the relevant data. 2. Efficient deletion. Upon receiving a deletion request, you can simply query for all rows associated with the unique identifier and delete them from BigQuery. This ensures that the personal data is fully removed from the database, complying with the legislation that mandates data deletion upon request. 3. Compliance. This approach ensures you can handle data deletion requests in a straightforward, efficient manner and comply with data protection regulations. Analysis of other options. Option B. Data Loss Prevention (DLP) API. While the DLP API can help you identify sensitive data in your BigQuery tables, it is not a direct solution for deleting specific individuals' data. It is more focused on detecting and classifying sensitive data rather than managing deletions. Additionally, Data Catalog is a metadata management service and does not help in performing the actual data deletions from BigQuery. Option C. BigQuery View. A view can help abstract the data, but it does not physically delete or anonymize the data. It only hides the rows from analysis but does not meet the requirement of ensuring that the data is completely deleted from the table. This solution may not be sufficient to comply with data deletion legislation, as it leaves the original data intact in the underlying table. Option D. Salted SHA-256 Overwrite. Overwriting the identifier with a salted SHA-256 value would anonymize the data but not fully remove it. While this can obscure the identity of the individual, it does not completely delete the data as required by law. The original data could still be present, making this approach non-compliant with data deletion requirements. Conclusion. Option A is the best approach because it ensures that upon a deletion request, the relevant data is fully removed from BigQuery using the unique identifier, guaranteeing compliance with data protection legislation. It provides a clear, efficient, and legally sound solution for handling deletion requests. Question 110. Your company has announced that they will be outsourcing operations functions. You want to allow developers to easily stage new versions of a cloud-based application in the production environment and allow the outsourced operations team to autonomously promote staged versions to production. You want to minimize the operational overhead of the solution. Which Google Cloud product should you migrate to? A. App Engine. B. GK On-Prem. C. Compute engine. D. Google Kubernetes engine. The best approach is A. App engine. Explanation. App Engine is a fully managed platform that abstracts away infrastructure management, which is ideal for scenarios where you want to minimize operational overhead while enabling easy staging and version promotion. It's designed to handle most operational tasks automatically, such as scaling, load balancing, and deploying new versions. 1. Ease of use for developers and operations teams. Developers can easily stage new versions in App Engine with simple deployment commands, and the outsourced operations team can autonomously promote versions to production with minimal effort. App Engine allows the operations team to focus on the deployment process rather than worrying about managing the infrastructure. 2. Automatic versioning and traffic management. App Engine supports versioning out of the box. Developers can deploy multiple versions of the application, and the operations team can manage traffic distribution between the versions. They can control the percentage of traffic going to each version, making it simple to roll out new versions incrementally and test them in production before fully promoting them. 3. Minimal operational overhead. App Engine automates the infrastructure management, so your operations team doesn't need to worry about configuring VMs, containers, or other resources. This minimizes the overhead and simplifies the operational process, which is critical when outsourcing operational functions. Analysis of other options. Option B. GK On-Prem. GK On-Prem is used to run Kubernetes clusters in on-premises environments, which involves more operational overhead compared to a fully managed solution like App Engine. GK On-Prem is typically used in hybrid cloud scenarios, so it's not ideal for a purely cloud-based solution where minimizing operational overhead is a key concern. Option C. Compute engine. Compute engine provides virtual machines that give full control over the environment. While this offers flexibility, it also requires more manual management, including handling infrastructure, scaling, and version promotion, which would increase operational overhead for the outsourced operations team. Option D. Google Kubernetes engine. GK is a fully managed Kubernetes service, providing more control and flexibility compared to App Engine. However, managing Kubernetes clusters and deployments requires more technical expertise and operational effort, especially in terms of configuring traffic management and version promotion. While it's a great option for complex applications, it involves more overhead than App Engine, making it less suitable if the goal is to minimize operational complexity. Conclusion. Option A, App Engine, is the best choice for minimizing operational overhead while allowing developers to easily stage new versions and outsourced operations teams to autonomously promote versions to production. App Engine handles the infrastructure management and simplifies versioning and deployment, making it ideal for this use case.